Okay, good evening. So, Erika didn't mention that I'm an engineer. And today I learned that a lot of people think that engineers are boring and confusing. So a smart cookie of my group told me, take cards, that you're not confusing all the time the people. Okay, let's try it, checked. And before I went here, my wife is a designer because I couldn't marry an engineer because two boring people is maybe not the best. She said, don't be boring. Okay, I won't be boring, hopefully. And yeah, considering that, I want to explain to you why it's so important to talk about sustainability in food and feed chains. And especially when we would consider this graph. Engineer loves graphs, so that's hopefully not so boring. This graph is showing a quite important challenge we have. It shows the energy equivalent of food. And you can see here heavy units, exa calories. Exa means 10 to the 18. That's a tremendous number, a 1 with 18 zeros. And in the last 500 years, we consumed 677 exa calories of food equivalent in the end, in terms of an energy unit. And in the next 50 years, it will be an almost similar number, around 720. So this is a clear challenge for us, especially from the food research environment, to tackle. And a lot of colleagues of mine, and to be honest, including me, we are very concerned about that, how we do that, and especially what happens if we can't supply enough food. So engineers, as mentioned, they like to first analyze then the system before they improve it. So let's take a look to our production of biomass and food. We go through different media, soil, water, and culture media. We have different sectors. Agriculture is the most intense one. And process and refine the biomass and food in different disciplines. And one quite important discipline here to consider for this talk is the Biorefinery principle. The closing cycles and use the residuals. We don't want to use food for bioenergy. This is not the best option for our point of view. We want to use the residuals to produce bioenergy because we need to have energy to produce food. The production marketing also includes the whole commercialization and the implementation, and that also needs to have business cases which are viable. And here you can see food, feed, bio-based products, and biofuel as well. And if we consider food, which is again the target of this talk today, we have three main components in food. It's carbohydrates, fats, and proteins. All are important. Some have some challenges, if you consume too much sugar, for example, too much fat. But we want to focus today on the protein supply, which is a concern because we need to have around worldwide 40 grams per day per human proteins available. Otherwise, we can't really survive. You can see here different age groups which need to have different amounts of proteins. And if we consider this 40 grams per day, which is a quite important value, and multiply that with 7.3 billion people on Earth, we need to produce 292 billion grams of protein per day. That's 292 thousands of tons per day protein. And we can only do that with resource investment, typical engineering term. Resource investment means we have only one planet. We have not two or more. Maybe we'll find more, but so far we have only one planet. And this planet has a specific amount of arable lands available. And here we can see on this graph what we need in terms of land use to produce 1 kilogram of protein with different sources. And you can see beef, quite tasty one. It's quite a lot land. And if we produce only beef, we can't supply enough food and protein, for sure. And one other extreme here is shown as algae, which is a quite interesting source because we can grow it on a very low amount of square meters to produce 1 kilogram of protein. And another important aspect is we can grow them on non-arable lands. Means we can grow them on this roof or on this surface which is sealed in front of this building. That means we can grow them in an urban environment within an urban farming concept. And that makes it very strong to consider to supply enough food with our very limited sources of land. Furthermore, algae protein has a very beneficial amino acid profile, because we cannot only think food is an energy equivalent that we do sport and so on. No, we need to have a healthy diet and nutrition, and so the amino acid profile is very relevant of proteins. And algae is a very good example here. Okay, let's go for algae. We are convinced. The problem is this production chain is not optimized yet. So we need to improve it to make it cost effective and affordable for a wide range of applications. And we believe we can do that with typical engineering aspects. We improve the processing in upstream and downstream. On the left, you can see the upstream part, where we work together with our partners on a new type of reactor system, which is called meshed ultra-thin layer systems. They work with a principle which is called surface volume ratio. A very beneficial surface volume ratio of a drop, which is dropping from the top to the bottom. There are different sieves. It's better than an open pond system, like in your bathroom, for example, or a tubular reactor. You have much better heat and mass transfer. That leads to a very important benefit. We can faster cool and faster heat the suspension, and we can also bring easier carbon dioxide into the algae because they love it. They accumulate it to oxygen and products. And we need to get out the oxygen because it becomes toxic for the algae. It's good for us, but for the algae it can become toxic. So we need to have a sufficient mass transfer. If this is improved, the whole cultivation is going much faster and we have much better production efficiency. And then we work on the right side on technology which is called electroporation within the downstream and the upstream, because with that we can make the algae, we can open the cells. We can open the cell membranes. It's called cell membrane permeabilization. We can open the cells and they will be open forever, or we can do a reversible process. And both combinations were implemented in our public funded project, which is called Innovative Algae Processing for New Proteins. And the good thing with this public funded project is you can join the discussion. So support us. One of the project managers is also sitting today in the room. And here we combined upstream, the new reactor system, with our electroporation technology to stress the cells with low energy input, to really we make a lot of physical stress on the cells that they increase their metabolic activity, that they produce more ingredients, which we are interested in, especially functional ingredients. And then we want to harvest this most of the time quite sensitive ingredients with, again, electroporation, but this time with higher energy input, opening the cells and get access to the sensitive proteins. I don't want to have a denaturated protein. When you cook an egg, you denaturate a protein. It's quite different. The egg first liquid, then solid. So I don't want to have the denaturated form. I want to have the native form. And that's why I need to have a gentle release process during extraction. So when we have access to this protein, we can produce other products. But before, first I need to check, are my technologies ready? We call that, as engineers, technology readiness level. That's a strange word. I can also tell you, technology readiness level means we have an idea, and you ask me tomorrow, okay, can we put it into a factory? If I say yes, technology readiness level is very high. If I say no, well, we need to have some money, blah, 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 then it's very low. So the technology readiness level of electroporation is very high, luckily. So we can implement our idea already in industrial scale, not really so fast as we expected, because that's production facilities worldwide, by the way, within the potato processing industry with our technology. So we need to adapt it a bit. But it goes still fast from our point of view. So our idea can be realized quite fast. That's a good information, especially for people which want to apply it. When we have access to the protein itself, we can produce ingredients out of it. And some ingredients are already implemented in confectionery products. A very nice blue colorant, for example. It's an algae protein within some Choco pills. I don't want to call the commercial name here. With a blue color and very small, kids love it. That's a algae protein, a phycobilly protein, phycocyanin. And the rest, we can apply a very interesting downstream technology which we also work on. It's high moisture extrusion technology to produce meat-like structures. Why we want to do that? We want to avoid the intense transformation of feed into animal protein, which is linked to tremendous environmental impacts. We produce a meat analog. It's not meat, but it looks like meat a bit when we add the right spices and put the right sauce to it. And it also tastes a bit like that. But it's labeled as meat analog. It's not labeled as meat, of course. We don't want to cheat the consumer. And here, this can be a quite interesting technology to avoid the whole complex animal breeding, etc., and all the linked environmental impacts to that. We can do that in a continuous mode and deliver some interesting products which are already on some test markets as well. Okay, when we simulate meat or imitate meat, we can also produce an animal protein, for example, or use an alternative animal protein source. And here we thought about, okay, what is available? What can be interesting as animal protein source? And here we thought about insects. You can see here on the left, dried insect larvae. Looks tasty. So who from you consumed already or is consuming insect-based products? That's around 5 people out of 100. I bet it's much more because you didn't consider honey. So I want to talk about honey production now. Just imagine, a bee is flying around. Eileen talked about the bee. Stopping by some leftovers from animals. Maybe then think about, okay, I will go now to the plant. Collecting nectars. But they're hanging around also some cooties, which also release some nectar. So the bee is communicating with the cooties, taking some nectar, taking the nectar into their bodies and digest it with their internal enzymes. That's already some special facts. However, then the bee is flying to their colleagues. And then they start the process which is called regurgitation. What is that? That's a kind of throwing up in front of their colleagues, smiling, and the others say, okay, that's great, and I take it up again. So they regurgitate and regurgitate again and again and again. They do that in a long chain till the honeycomb. And then the honey product is coming to your breakfast. So let's talk about honey now. And let's talk about the reputation of insect-based products. I recommend to you, talk with your families tomorrow morning during breakfast. Observe their face change. And then you understand the main hurdle why we cannot, or why the main innovation hurdle where we struggle to implement insect-based products into the food and feed consumption. So you might understand it a bit. But insects are a great source of proteins because of their very efficient cultivation and because of their very high ratio of edible parts. And this makes it a bit more obvious, this overview, our little calculation. What can we achieve with 100 grams of feed? So we can give it to a beef or a cow, pork, poultry production, or we can give it to our insects. And they convert it much more efficient into live animals. And then they have a very high ratio of edible parts as well, the highest from the whole group. And then they have also the highest protein content of the edible parts, up to 77%. And that makes it very strong, because remember the 40 grams per day per human. We can feed with this 100 grams of feed, finally, 430 humans with animal protein per day. With a cow chain, we would only have 12. And I guess that's very strong. So let's talk about how we can implement all these nice ideas from engineers, scientists, it's teamwork, of course, into one sustainable value chain. And here we developed the novel protein biorefinery concept, where we want to use byproducts from food production, and we have a lot of it. We throw away a lot, we put it to biogas, but we can also use it for algae cultivation with our new reactor system in an urban environment without any arable land use. We can apply our new electroporation technology to get access to the sensitive ingredients of the algae. The residuals are then going through our biorefinery approach to produce enough bioenergy, because our production takes energy. And then we have this nice food plant proteins, which can be divided into high value added products, for example, colorants, where we can afford where we can get a high price to justify our investment, because we first need to invest into such value chain. And then we have the bulk proteins, which are quite high ratio as well, up to 70% in algae, dry matter. And this can be extruded to meat analogs, for example, again. So we have this value chain also possible. However, we still need to have the classical animal proteins available because the consumer wants to have it. How we can do it more sustainable, we make an insect loop for feed. For the feed supply of our poultry, salmon, and pork production. And yes, we need to also kill an animal to produce animal protein. By the way, the insects will be also killed. They won't survive in your stomach. And then we take again the leftovers and the residuals to produce reformulated proteins. We need to use all proteins because we don't have the luxury to waste them. So this concept is not implemented yet. It's very challenging, a lot of hurdles, a lot of bottlenecks. I know all the stories. However, we believe it could contribute to our big challenge from the first slide for an interdisciplinary solution to tackle our future food supply. But there's one important aspect to consider. We need to start the research and development now. Thank you.